We'll start in about 3 minutes. All right, we'll continue the test 2 review today. We got to this problem yesterday. Find the surface area of y equals the natural log of x for values of x between 1 and e by rotating about the y-axis. So our surface area on the interval from 1 to e is 2 pi x times the square root of 1 plus dy dx squared. So the function y is y equals the natural log of x. So we have to find the derivative, which is 1 over x. And then 1 plus the derivative squared is 1 plus 1 over x squared. But I'll write this as a single rational expression, which is x squared plus 1 over x squared. This will be what goes inside the square root. And then dx. Hey, in the integrand, we have a factor of x, and we also have x squared in the denominator of the square root. So those are going to cancel each other out since the square root of x squared in the denominator is x. So in the next step, I'll bring the 2 pi out front of the integral from 1 to e. And then we have the square root of x squared plus 1 dx. So I wonder if I brought extra scratch pieces. So I might need a little more space on this one. So what are we going to do? The integrand is the square root of x squared plus 1. Yeah, we can use a trig substitution. The one to use in this case is x equals tangent of u. So remember, when you're doing a trig substitution, you want to have tangent of a different variable than x. If you write x equals tangent of x, then you're using x for two different quantities. So that will get you into trouble. So we'll define x to be the tangent of u, and dx is secant squared of u du. So we'll transform this integral. So note that if x is tangent of u, x squared plus 1 is tangent of u squared plus 1. I guess I can write it. I'm going to have to probably use extra space anyway. So x squared plus 1 is tangent of u squared plus 1. But tangent of u squared plus 1 is secant of u squared. And then when we take the square root of secant of u squared, this will become secant of u, right? Do you want me to write it down, or could you see that?
Where's your factor? That's the trig identity, right? The tangent squared turns into secant.
Yeah, tangent of u squared plus 1 is equal to secant of u squared. That's one of the Pythagorean identities. So I'll go ahead. We'll have to alter the, we'll have to change the limits of integration since we're doing this transformation. But since x squared plus 1 becomes secant of u squared, we have the square root of secant of u squared. And then we're replacing dx with secant of u squared. And then the limits of integration. So here is our trig substitution, x equals tangent of u. In the original integral, the limits are x values. So when x is 1, we set 1 equal to tangent of u, and what value of u is the tangent equal to 1? Yeah, so the inverse tangent of 1 is what u is equal to, but that's equal to pi over 4, right? Tangent of pi over 4. So the lower limit on this integral will be pi over 4. And then on the original integral, the upper limit is x equals e. So for now, we'll just say since e is equal to tangent of u, we'll just say the upper limit is the inverse tangent of e. And we'll deal with that in a couple of minutes. So the upper limit is the inverse tangent of e. Okay, but I need more space, so So before I remove this page, just note what's going to happen in the integrand. When we take the square root of secant of u squared, we get secant of u, and secant of u times secant of u squared is secant of u to the third. Okay, so that is this integral here. And we've seen the integral of secant of u to the third du before. We probably didn't use the variable u, but that's just a happenstance. Okay, so I'll just remind you of what an antiderivative of secant of u to the third is. So this will be s equals 2 pi. And then we get 1/2 times the quantity, the natural log of secant of u plus tangent of u plus the product of secant of u and tangent of u. And then we're going to evaluate this from u equals pi over 4 up to u equals the inverse tangent of e. Okay, let's do some right triangle trigonometry. If the inverse tangent of e, what does that mean? The inverse tangent of e is the angle whose tangent is equal to e. So if this is our angle and the tangent is e, then opposite over adjacent is e over 1, and the hypotenuse is the square root of e to the second plus 1. So this angle right here is the inverse tangent of e. So we can find the secant of u as well as the tangent of u. So our surface area is 2 pi. Oh, let's multiply 2 pi times 1/2 just to write pi. And then we'll have the natural log of secant of u. So here's the u. What's the secant of that angle? That's the reciprocal of cosine, so it's the square root of e squared plus 1 over 1. So this is the square root of e to the second plus 1. And then plus the tangent of u, which is e over 1, or e. And then plus the product of secant of u and tangent of u. So that will be the square root of e squared plus 1 times e, but I'll write it as e times the square root of e to the second plus 1. Okay, so that's the upper limit, and then we subtract what we get from the lower limit. The lower limit is pi over 4. So secant of pi over 4 is the square root of 2. Sorry, I need minus the natural log of this. The natural log of secant of u is the square root of 2 plus 1. And then we're adding that to secant of u, tangent of u, which is the square root of 2 times 1. Okay, so let me write this so that it looks a little more organized. So the surface area is pi times the natural log of the square root of e to the second plus 1 plus e times the square root of e to the second plus 1. And then we're subtracting these terms, so we're subtracting the natural log of the square root of 2 plus 1, and we're also subtracting the square root of 2. Okay, let's move on to the next page on the test 2 review. Yeah, this one, a vertically oriented 4 feet by 8 feet rectangular plate is submerged in water. A short side, meaning the 4 feet side, is at the top, and it's 3 feet below the surface. Find the hydrostatic force on one side of the plate. So we have the water level, surface of the water, and then a rectangular plate. It's 4 feet by 8 feet. And the top of the plate is 3 feet below the surface. And so at the bottom, we're at a distance of 11 feet below the surface. So if we subdivide the rectangle into smaller rectangles, each of width delta x. So what we're doing is I'm using the positive x values downward. So at the top, we have x equals 0. And then as we go deeper, the x values become positive. So if we're at a depth of, say, x sub I, then we want to find the hydrostatic force on that little rectangle. So for the ith rectangle, the hydrostatic force is the density times the gravitational constant multiplied by the area of that rectangle times the depth at that rectangle. Okay, so in this picture, the depth is x sub I. That's x sub I feet below the surface. And the area of that rectangle, well, it's 4 times delta x. And since the dimensions of the rectangle are given in feet, rho times g is 62.5 pounds per square foot. Okay, so then upon substitution, the hydrostatic force on the ith rectangle out of n rectangles total is 62.5. We'll write 4 times x sub I times delta x. And if we do that for all of the rectangles, and then take the limit, then the hydrostatic force is the definite integral from 3 to 11.
I have a question.
What's that?
Can you explain why AI is 4 times delta x?
Yeah, the area of the rectangle, the area of this rectangle. So one side is 4 feet and the other side is delta x. So yeah, a sub I is the area of that rectangle. And d sub I is the depth, which is x sub I. That's x sub I feet below the surface. Okay, so in our Riemann sums, we have one of these for each I between I equals 1 and n. And we add those up and then take the limit, we get this definite integral. So I'll go ahead and write it as 62.5 times 4 x dx. And we can simplify this a little bit because 4 times 62.5 is 250. So we get f equals the constant 250 times the integral from 3 to 11 of x dx. And this is a pretty simple integral to evaluate. So we get 250 x to the second over 2 from 3 to 11. 250 divided by 2 is 125. And then 11 squared minus 3 squared is 121 minus 9, or 112. So multiply those together, and this will be measured in pounds. So I guess we can do that. This is 12,500 plus 1250 plus 250. So that's a total of 1,400 pounds. Is that what you get for the hydrostatic force on one side of the plate? Yeah.
Question. For test 2, are we going to want to make sure to be familiar with values like that 62.5? Or is that something that might be provided in the question itself?
Yeah, the question is, will you be expected to remember that rho times g is 62.5? Well, I thought so.
It's just good to know.
But I'll consider giving it, like if I have to, or if I think that it's warranted on a test. But it's not too hard to remember. When feet are involved, that is 62.5 pounds per cubic foot. But yeah, I think I'll do that. If on a test, I'll give you the values of rho times g. Okay, the next problem, find the centroid of the region bounded by the square root of x, y equals the square root of x, and y equals x. Well, we need to know where they intersect. This one is not too hard to figure out. The graphs of those intersect at 0, 0, and 1, 1. So y equals the square root of x looks something like that, and y equals x. Looks something like this, and we want to find the centroid that's in the region bounded by those two curves between 0 and 1. Hey, the moment of the region about the y-axis, well, we have this density constant rho multiplied by the definite integral from 0 to 1, and it's x times the difference of the two functions, x times the quantity square root of x minus x dx. So the formula, if you, this formula you should know in general. It's rho times the definite integral from a to b of x times f of x minus g of x dx. Okay, so we can rewrite the integrand. X times the square root of x is the same as x to the 3/2. And then minus x times x is minus x squared. So we evaluate this. We get x to the 5/2 divided by 5/2, which is 2/5 times x to the 5/2 minus 1/3 times x to the 3rd, evaluated between 0 and 1. So we're going to get rho times 2/5 minus 1/3 . And so the moment of the region about the y-axis is just going to be rho times 1/15. Okay, then the moment of the region about the x-axis. Okay, this is rho times the definite integral from 0 to 1 of 1/2 times the quantity, the square root of x squared minus x squared. Okay, so this formula, in general, the moment of the region about the x-axis. Yeah, so it's rho times the definite integral from a to b of 1/2. And then you have to square the function f of x. And then from it, subtract the square of g of x dx. Okay, so we got rho times 1/2 well, we'll have to do a little bit in our heads. When we square the square root of x, we get x, and then an antiderivative of that is 1/2 x squared. And then an antiderivative of x squared is 1/3 x to the 3rd. And we're evaluating this from 0 to 1. So rho times 1/2. And then in the brackets, we have 1/2 minus 1/3. 1/2 minus 1/3 is 1/6. And so rho times 1/2 times 1/6 is rho times 1/12. Okay, then we find the mass of the region. So the mass of the region is rho times the area in that region. So the area is the integral from 0 to 1 of the square root of x minus x. Okay, an antiderivative of the square root of x is 2/3 times x to the 3/2, and then minus x squared over 2 from 0 to 1. So we get rho times 2/3 minus 1/2, which is 1/6. So rho times 1/6 is rho times 1/6. Okay, then finally the x bar, that's the x coordinate of the centroid. That's the moment of the region about the y-axis divided by the mass. So we found the moment of the region about the y-axis, rho times 1/15, and the mass is rho times 1/6. So we'll go ahead and ignore rho's since they cancel each other out, and 1/15 divided by 1/6 is 1/15 times 6 over 1, and that becomes 2/5 for the x coordinate. And then the y coordinate of the centroid is the moment about the x-axis divided by the mass. So rho times 1/12 divided by rho times 1/6. So the rho's cancel. 1/12 divided by 1/6 is the same as 1/12 times 6 over 1. So we get 1/2. Okay, the answer looks reasonable. The point 2/5, 1/2 looks like it's in the region. So 2/5, 1/2 is what I got for the centroid. Okay, moving on to the next problem. We have a differential equation. Solve the initial value problem. X times y prime equals x plus 1, where y of 1 equals 0. Okay, I'm going to start by dividing both sides by x, and then I'm going to replace y prime with dy dx. And then x plus 1 divided by x, I'll write it as two separate terms. So x divided by x is 1, and then plus 1 over x. So we can separate this. This is separable. So what is meant by separable? Well, if we have all of the terms that have the variable y on one side and all of the terms that have the variable x on the other, including the dy and the dx, then it's separable. So if we just multiply both sides by dx, we get dy equals the quantity 1 plus 1 over x dx. And then what do we do? Now that it's separated, then we integrate both sides. So the integral of dy, that's like 1 dy, equals the integral of 1 plus 1 over x dx. And an antiderivative of 1 with respect to y is y. And then we integrate the right-hand side with respect to x, and we get x plus the natural log of the absolute value of x plus a constant. And then to determine what the constant is, we use the initial value, and that means that when x is 1, y is 0. So replace y with 0, and replace x with 1. The natural log of 1 is 0, so we get 0 equals 1 plus c, and this implies c is equal to -1. So our function that we solve for is y equals x plus the natural log of the absolute value of x plus c. If you can read that.
C would be -1.
Oh, duh, yeah. That was the whole point of that. Yeah, y equals x plus the natural log of the absolute value of x minus 1. So there is our function. Okay, the next one, number 9. A mixture problem. A 50-gallon tank is filled with salt solution that has 12 pounds of dissolved salt. And then a salt solution containing 0.5 pounds of salt per gallon is added to the tank at a rate of 1 gallon per minute, and it's drained out at the same rate. So an assumption that I didn't write in there is that it's assumed that the solution in the tank is thoroughly mixed, so that everything in the tank has a equal percentage of salt. Okay, then find a function that measures the amount of salt in the tank after t minutes. Okay, so I'll define s of t to measure the pounds of salt in the tank at time t minutes. So the amount of salt, dissolved salt in pounds, at time t minutes. So we observe, since we're starting out with 12 pounds in the 50-gallon tank, S of 0 is 12. That's like an initial value. And we're given information about the rate of change of the amount of salt per minute. So in other words, the rate ds dt. So we have a rate going in and a rate going out. Okay, the rate in, salt solution containing 0.5 pounds of salt per gallon is added to the tank at a rate of 1 gallon per minute. So for this first time, I'll write down the units. So the salt is coming in at 0.5 pounds per gallon at a rate of 1 gallon per minute. So the gallons units cancels, so we interpret this as salt is being added to the tank at the rate of 1/2 of a pound per minute, right? And then the tank is also being drained at the same rate. So what should I subtract?
So over 50 times 0.5.
Yeah, so at time t, S of t represents the amount of salt in the tank at time t. And so the percentage, the decimal form of the percent of salt at time t is S of t divided by 50. So S of t, this is the pounds of salt divided by 50 gallons. So this represents the decimal form of the percent of salt that's in the tank at time t. And then we multiply that by 1 gallon per minute. The gallons units cancel, so this indicates the rate at which salt is being taken out of the tank at time t. Okay, so if we ignore the units, then we can write ds dt equals 0.5. I'm going to write that as 5/10, 5/10 for now, and then minus S over 50. And then a common denominator is 50. So I'll write ds dt is equal to, in the numerator, 25 minus S, and in the denominator, 50. Okay, so this is a separable differential equation. The variable t doesn't appear, but that's okay. So if we separate this, we write ds over 25 minus s, and then on the right-hand side, 1/50th times dt. Then we integrate both sides. On the left-hand side, we integrate with respect to s. We're going to get the negative of the natural log of 25 minus s. And on the right-hand side, we get 1/50th t plus a constant. So I need more space, so I'll continue this on another piece of paper here in a second. Okay, so we're at this point, and then here's a reminder of the initial value. Okay, so if we multiply both sides by -1, we get the natural log of 25 minus s equals -1/50th t minus c. And then 25 minus s equals e to the, I'm going to write e to the -c times e to the -1/50th t. I'm just using properties of exponents to write it that way. And then when we solve for s, add s to both sides, subtract this, we get s equals 25 minus e to the -c times e to the -1/50th t. And then we use the initial value s of 0 equals 12. So when t is 0, this quantity is 12. So when t is 0, s is 12. So we get 12 equals 25 minus e to the -c times 1. When t is 0, this term is 1. So from this, we see that e to the -c is just 13. So our function is s equals 25 minus 13 times e to the -1/50t. If you can read that. It looks pretty botched on the computer screen, so I'll rewrite it. Hey, that's our function.
Excuse me, Professor, I do have one question. I don't know if I was able to follow. Why is it that the natural log of 25 minus s was negative after we integrated it? Up the very top.
Because we were integrating ds over 25 minus s. If u is 25 minus s, then du is -1
Oh, okay.
ds. So I compensated by, I just basically skipped a step. I put a negative so that we had a negative ds, compensated by multiplying -1 on the outside.
Okay, thank you.
So we have a few minutes. If I might go into a little more detail in that in a couple of minutes. Let's see if we can finish this problem 10. Solve the equation y prime plus y over x equals 2 over 3 times x to the 1/3. Okay, so this is a first order linear. This has the form y prime plus p of x times y equals q of x. So it's a first order linear. And so our p of x is 1 over x. And so our integrating factor is e to the integral of 1 over x dx. An integral of, or an antiderivative of 1 over x is the natural log of x. And e to the natural log of x is x. So we'll multiply every term on both sides of this by x. And we get x times y prime. And then x times y over x is just y. And on the right-hand side, when we multiply x times 2 over 3 times x to the 1/3, we'll get 2/3 times x to the 2/3 when we multiply that by x, right? So if I multiply that by x, I get 2x over 3 times x to the 1/3. Think of x as x to the 3/3. So it becomes 2 times x to the 2/3 over 3, right? Okay, the left-hand side is the derivative with respect to x of x times y. So then we take the antiderivative of both sides. The antiderivative of the derivative of x times y is just x times y. And then an antiderivative of 2/3 times x to the 2/3 is 2/3 times x to the 5/3 divided by 5/3. But if we divide by 5/3, we multiply by 3/5. So we get 2/3 times 3/5 times x to the 5/3 plus a constant. So in the next step, I'll do a couple of things. I'll simplify the 3 divided by 3 and also divide every term on both sides by x. So we get y equals 2/5 times x to the 2/3 plus c divided by x. And then the initial value, y of 1 equals 1. So when x is 1, y is 1. So we get 1 equals 2/5 times 1 plus c over 1. This implies that c is equal to 3/5. So our function then is y equals 2/5 times x to the 2/3. And then instead of c over x, we can write it as 3 over 5x if you want. Hey, that's all we have time for today. If you want to stay for a minute, I can explain that negative thing.
That's okay. Unfortunately, I can't. I appreciate the offer though.
Okay. Okay, tomorrow we'll do the other test 2 review sheet as much as we can.